So it's my great pleasure to have Katy here, Katy Clough, as our first speaker. Katy is based at Queen Mary University of London, and she will tell us about new fundamental fields in strong gravity. Please, Katy, thank you.
Thanks very much, Laura. Okay, so I'm very happy to be here. Thanks, really, very many thanks to the organizers who seem to have done an enormous amount of work in organizing this conference. Let me just sort of get started. So when I was invited to this conference, I kind of didn't know what to talk about because it's both dark matter and it mentions sort of modified gravity as well. And I worked a bit on both of those things. So I thought, well, actually, I don't really know what to talk about. So I decided rather ambitiously to talk about both things. So what I thought would be nice in the context of the conference is to really kind of contrast the two things. So I want to talk about fields, so fields in strong gravity, and we will hear a lot more about fields in strong gravity from other talks. And what we'll hear is that sometimes fields can be, firstly, an effective description of dark matter, so particularly in cases where the dark matter has a de Broglie wavelength, which is sort of macroscopic, which is large on some astrophysical scale, and we can sometimes call that wave dark matter. But it can also be an additional degree of freedom in a modified gravity theory. So in a sense, both of these things are just adding a scalar field to gravity. And so you might think that they're quite similar, and certainly in some ways they are. But actually the challenges in these two cases can be quite different, particularly in the case of simulating them in strong gravity environments, which is what I'm going to talk about. So the basic question that we want to answer with the type of simulations that I do in numerical relativity are, how might the presence of these extra fields affect the merger part of the waveform, so this part of the waveform that's seen in things like LIGO. So what we might hope is that, by having this additional stuff around, this signal doesn't do this, it does this. It does something crazy, around the merger. And it might have some sort of distinctive signature that we could notice, and we could say, okay, this matches what we expect from X modified gravity theory. So unfortunately, because... Oh, it's gone to sleep. It's okay. So of course, because we know that modifications to gravity are relatively weak because we don't see any sign of modified gravity in a lot of the observations we make, actually the change is going to be a lot more subtle than that. It's not going to be like some crazy bump in the waveform, or at least that's very unlikely. It's going to probably be something more like a slow dephasing of the signal. And so we need to model that and model it well in order to be able to distinguish it from other effects. So yeah, the questions I really want to answer is, how might these effects, how do these effects affect the waveform, and what are the research challenges, particularly for numerical relativity in each of these cases? So okay, I'll start with a bit of background. So firstly, why would the waveform change due to having new field content around? So the kind of most basic mechanisms are things that are quite sort of really just nice, solid physics. So things like radiation of the environment. So, especially if the fields are quite light, they will be radiated by the motion of the binary. You also have a dynamical friction, where you accumulate some overdensity of the field behind the object, which gives you a gravitational drag force. You also have accretion of the field onto the objects, which would change their mass over time. Then another thing that needs to be modeled is the fact that actually if you put stuff around a black hole, it's no longer a pure black hole space-time. So we know that matter curves space-time, so the space-time will be curved by the presence of this additional stuff. And especially if it has a kind of distinctive shape or distinctive distribution, that might provide you with some kind of signature. And then I've put this kind of higher order curvature effect. So in modified gravity, kind of all the rules of physics, as you know, are not necessarily what you think they are. So in particular, you have sometimes something that's like an effective negative energy density that comes from curvature terms. And so things that you thought were kind of rules of physics, like the irreducible mass of black holes, is no longer irreducible and can change over time. So these kind of things could give you distinctive signatures. So let me first talk a little bit about modified gravity. So I like this slide very much, that I've stolen from someone else's paper. So there are many ways to modify general relativity. So, you know, we could give the graviton a mass, we could break some symmetries, but probably the kind of the simplest thing is to add an additional field content that perhaps is some, you know, could still, may not be the fundamental theory of gravity, but is some effective field theory of gravity coming from string theory or you know, something like that. So adding additional fields is something that's quite common in modified gravity theories. So you might want to know, well, okay, maybe we should have already seen this because we have lots of observations from different sources. So I won't name all of the things on this slide. I don't think you can see my pointer, but there are some things that are like SS, I think is solar system constraints. So on this plot, I really like this plot, but the axes are a bit hard to figure out. So on the horizontal axis, you have the potential, and what that really tells you is how close are you getting to the Schwarzschild radius of this object. So you can see there's kind of a hard line on the right-hand side that's sort of basically at the Schwarzschild radius. And going away from that, you're getting sort of more into a sort of weak field regime. Is it all right?
Yeah, there is a laser pointer if you like to.
Oh, okay. Thank you, yeah. That.
Should already be.
Great, thank you very much. Yeah, so this is what I was saying. Yeah, these are the solar system constraints. So yeah, this horizontal axis is this idea of how close are we to the Schwarzschild radius, and then this vertical one is basically the Kretschmann scalar, so the square of the Riemann tensor that tells you something about how strong the curvature is in that regime. And so you can naturally relate this to a length scale, which I've sort of put on the right-hand side. And, you know, at the bottom, you know, we've got a kind of fundamental limit, which is our universe. We can't really observe things with a curvature scale larger than our universe. And then, you know, we have the kind of the supermassive black hole length scales here. And I guess the point that I want to make is that right here at the top, this is what we're probing with neutron stars and sort of solar mass black holes. And it's a new regime that doesn't fall into any of these other constraints. So you would hope to be able to potentially see something new here. Of course, there's no reason why you have to see anything new here. It could be that the scale of new physics is you know, way up off this plot vertically. So then you would need something like a primordial black hole to be able to probe those kind of curvature scales. But you know, we can at least hope that this is a new regime to look at, and so we might find something there. So yeah, just to give one example, there's this particular flavor of modified gravity theory, shift symmetric Einstein scalar Gauss-Bonnet, and that's quite strongly constrained by the LIGO observations so far. In particular, you have a kind of coupling scale in your theory, and this acts on the scale of, I think it's going to die again. So yeah, this acts kind of on the scale of the Schwarzschild radius of your object, and so actually it's a stronger effect for smaller mass black holes. And so actually it's already not possible to have these kind of modifications on the scale of supermassive black holes. So in a sense, these theories are more of interest for like LIGO-type observations, LIGO-type frequencies, than they are for LISA-type observations. Except in LISA, you can have MREs, and then the smaller object could, have these effects. So yeah, so it's really of interest for smaller mass black holes. Okay, what about dark matter then? So let's, we're sort of switching between the two. So this is like a field that I'm thinking of as being an extra degree of freedom in gravity. But if we add a field as our dark matter, so it turns out that, naively, I think you wouldn't think that an additional scalar field could behave like dark matter. But actually, if it's very cold, if it's very homogeneous, the field, it can actually mimic dark matter on the large scales that we observe. And that's where we really, where we do have good observations of dark matter. So this picture that I'm showing here is a simulation where you've done it with kind of standard cold dark matter, and then you've done it with this fuzzy or wave dark matter. And, basically you're supposed to see that they look roughly the same. So on large scales, they're very similar, but then you get differences on smaller scales. And what's of particular interest is that, these are cosmological scales, But once you then go down to the scales of black holes and the Schwarzschild radius, something that has a very long de Broglie wavelength compared to the Schwarzschild radius of the black hole, you're going to have quite strong wave effects in that regime. So if you think that dark matter, has a very sort of small mass and therefore has a very large de Broglie wavelength, you can get these nice wavy effects around your black holes, which I will show some nice movies of in a bit. So again, I would like to ask, would we have seen this already? Should we already be expecting to measure some signature of dark matter in our gravitational wave signals? And I would say, not in standard dark matter scenarios. So I don't know how many particle physicists and astrophysicists we have in the room. I don't know what the split is, but you will recognize one of these numbers as being the average dark matter density in galaxies. And I like to translate this for the numerical relativity people. So the interesting thing about expressing it in these units are basically the code units. So when I would simulate dark matter around a black hole, what number would I put into my simulation to represent the dark matter density if my black hole has a mass of 1 in my code units? You see that this number is 10 to the minus 30. So that's way below numerical precision in my simulation. So I don't need to run a simulation to tell you that this won't have any effect, right? Like it won't even register in my simulation. So you need some kind of mechanism that enhances the density of the dark matter around the black holes. And there are well-motivated scenarios in which that would happen. So I think we're going to hear about superradiance next, but I also wanted to mention accretion of this wave-like dark matter onto binaries. And in those cases, the constraints are entirely dependent on what you believe the local dark matter density is. And that's something that we don't necessarily have a great deal of information on. We have it on sort of galaxy scales, but we don't necessarily know around a black hole or locally to black holes, is there any kind of clumpiness in the dark matter? So in this case, if you look at the scaling that oh, it's got stuck. Sorry, I didn't notice. Yeah, let me unplug and replug. I think it's maybe take this out. Okay, great. Okay, I'm just testing all the technical equipment for the people who follow, so don't worry. Yeah. Okay, yeah. Oh, so you missed my nice picture of, it's because I'm looking at it here. So yeah, this is the sort of the cosmological picture of the dark matter where they look the same. And yeah, these were the numbers that you should have been seeing comparing the dark matter densities. And yeah, as I say, this is the number for numerical relativity people, which is, as I said, about like 10 to the minus 30 in some of these units. So yeah, you need some enhancement of this number in order to be able to see some effect. Okay, so how do we work out how much things change? So I mean, this is a completely biased view. There are actually many ways to work out these effects, but I will focus on numerical relativity because that's what I work on. And this is, obviously useful and important for the late in-spiral merger phase, and really focused on approximately equal mass objects. So it's difficult to go beyond a mass ratio of about 1 to 10 with numerical relativity. So what's the goal of numerical relativity? The goal of numerical relativity is to try and actually find out what the metric of space-time is at all points in space and time. But due to finite computational resources, we obviously don't simulate the entire universe for the whole history of time. We have to do this in a kind of finite region of space and time. So we have to put in some initial data at some finite time before, in the case of a binary merger, before the binary merger happens. We have to apply some boundary conditions in space, unless we're clever and we can do things that go all the way out to asymptotic infinity, which is something that's worked on here. And then we want to fill all of this region of space and time using the Einstein equations to, as I say, to understand what the values of the metric are there. So I always give this example that I always say is a bit trivial, that, imagine putting a single black hole into your simulation, you put the Schwarzschild metric as your initial conditions, your boundary conditions are asymptotically flat space, and then you evolve it forward in time. Well, if it was the Schwarzschild metric in principle, because it's a stationary solution, you would just see the black hole sitting there and nothing would happen. It would be a very boring simulation. But actually, this isn't. And it was pointed out to me by Deirdre Shoemaker, who was one of the original people who figured out how to do this numerically, that this isn't at all a trivial thing to do, and it actually took them like 10 years to figure out how to get this to work. So I shouldn't say that it's trivial. It turns out that it's quite difficult, simply because at least the naive way that you write down the equations, the ADM equations for the decomposition of space and time, is not well posed. So that means it's not stable for numerical evolution. You don't have necessarily a unique solution. So it took people a long time to figure out how to do this correctly. So the two key challenges that I want to highlight, and I'll come back to these in the context of the fundamental fields, are that it's really non-trivial to find the initial data. Solving the initial data for these simulations is kind of a computational challenge in itself. And then, even once you've done that, then finding well-posed formulations of evolution equations, finding, the way to evolve it stably is again, kind of a non-trivial problem. So something that I won't talk about at all is the sort of the end product, right? So the whole goal of this would be to generate a load of waveforms and then do some data analysis on it. And then you would have to worry about, even if I can see these effects in the waveforms, are they degenerate with other things? And I'm just going to completely skip over that because I don't have time. And we're not at that stage yet. I think we're still trying to figure out just how to get these simulations kind of working and correct before we start doing necessarily all of that data analysis. Okay, so let me finally come to talking about the specific challenges for each of these cases, for modified gravity and for dark matter. And yeah, I'll split it into two things, which is initial conditions and then the evolutions themselves. And so basically what I'm going to say is I think that initial conditions are more of a problem for the dark matter case, whereas the evolutions are more of a challenge for the modified gravity case. So I think they have different challenges. But let me just put up this slide that I made. I mean, the coloring is slightly arbitrary. I think it's an exaggeration in all the cases. Like green, okay, is not necessarily really okay. It's still kind of challenging in some cases. But broadly speaking, for modified gravity, your initial conditions for your black holes, if your black holes have some of this scalar field hair around them at the beginning of your simulation, that's quite well defined by the theory that you pick. So I think in a sense, once you tell me what your modified gravity theory is, it's quite easy for me to go and work out what the initial conditions should be. And I think the second point is the really important one, is that usually that sort of fundamental field environment around the black hole is quite localized close to the horizon of the black hole because it's sourced by the curvature of the black hole. And so usually you can superpose two isolated solutions, so have one black hole with hair here, one black hole here, and you can just superpose them to get the binary, and that's not too much of a bad approximation. Whereas in the case of dark matter, the distributions tend to be much more fluffy. They tend to be much more extended around the black holes, and so superposing them, I'll show you in an example in a bit, is just not going to be the right thing to do. Like, they interfere with each other in such a way that the pattern you get is completely different once you superpose them. So So then once you've done that, you have to do this solution of the constraint equations for general relativity, so basically energy and momentum conservation in your initial conditions. And that is okay to do for the dark matter case. It's something that hasn't yet been done for these modified gravity theories. People generally cheat, it's not cheating, but they start with like zero field and then they evolve, they evolve the hair from zero, or they superpose something that violates the constraints and they rely on some damping of the constraints to give them the initial conditions. But although that's unsolved, I actually think it's relatively straightforward to solve it. It's just that no one's really tried that hard to do it. So yeah. Oh, does that mean my time's up? Okay. All right. I don't have that much time to tell you about these things. So I was just going to tell you, let me just show you my nice movies. So this is the accretion of dark matter in the wave-like case on a single black hole. And so what I wanted to tell you, which I just mentioned, is that actually once you put a binary together, you don't get something that looks like this. You get something that's a real kind of interference, a sort of swirly interference pattern between the black holes. So it does actually, so on the left is the field, and the field has a wave-like behavior, so it oscillates. And on the right is the energy density of the field, which is the thing that's really going to drive any kind of changes in the waveform. And you see that you do get an overdensity forming between the black holes. But this solution, I can't write this solution down. This solution, unlike the isolated black hole case, is not in Mathematica. It's not one of the Hoym functions or something like that. Like, I need to evolve this to be able to get this. So to actually start my simulation, I can put in like lots of different types of initial condition, and they will give me different results. Whereas I really want to start with this kind of stationary solution for the field that would be there, had I been evolving it from the beginning of time. Okay, I'll just tell you the punchline for the evolution of fields for the modified gravity, since I'm almost out of time. So in this case, I wanted to say that I think it's more challenging in the modified gravity case for the evolution, mainly because we don't have well-posed formulations for most of the modified gravity theories. In fact, we only really have them for the scalar field cases at the bottom, and even that was a relatively recent development by a group in Cambridge who wrote down a solution which allowed us then to go ahead and do simulations of black holes in modified gravity environments. And before wrapping up, I'll just show you this nice story of what can happen in these modified gravity theories. So what can happen is that actually you can have the modified gravity effects turning on due to spin. So in this case, you see in the top row, you get this is the ring down of the black hole. And so it rings down, and then you have a spinning black hole. And so then this actually generates a burst of this scalar modified gravity extra field. You get a burst of this scalar gravitational wave radiation. And the scalar field grows at the horizon. And the black hole in the next line, you can see, spins down a bit. So some of the spin is extracted to develop this scalar hair. So that what you would like to do with this is you would actually like to kind of push these effects closer together, because actually there's no modification here to the tensor part of the gravitational waveform because they don't overlap, these effects. So everything is basically GR whilst the merger and ring down is going on. But in order to push these effects closer together, you need to really turn up the coupling on the modified gravity theory. And at some point, your evolution becomes ill-posed. The well-posedness of your equations breaks down because you're in the strong coupling regime. So you have this kind of challenge between wanting to see the effects, wanting to make the effects stronger, and actually being able to evolve it stably. And this is why this is the main challenge for modified gravity. Okay, then since I'm vastly over time, I will just summarize. So I think beyond GR effects, it's exciting that they're now potentially detectable from both dark matter and modified gravity. So developments in initial data and this well-posed formulations has really been quite exciting in recent years. You know, it's meant that these numerical relativity tools can be, you know, can actually tackle at least some of these effects. But I think the thing that is the real elephant in the room is that there is a whole zoo of possible scenarios and couplings and, you know, effects. And in a way, we have to work out, you know, where do we focus our efforts on these things. And I'll stop there. Thank you.
Yeah, thank you very much for the very nice talk. We have time for questions now. So who has a question? All right. Alfonso, could you please take the other microphone? I've seen you first. We start over here and then go row by row.
Yeah, thank you very much for the very nice talk. So, so modified gravity and dark matter, actually, they can be one problem or they can be two problems. Because if dark matter is minimally coupled to gravity, then we can basically treat it as matters, and you know, just in the T mu nu, not in the G mu nu. But as you show in some cases, for example, the Einstein scalar correspondence theory, the coupling is non-minimal, and you then have to treat it as a modified gravity. So from your perspective on numerical relativity, what is the, you know, the most economical way to you know, track down this kind of problems? You know, you want to treat this you know, in a very broad sense, or just show some special cases? Thank you very much.
Yeah, so you're exactly right. So in a sense, the dark matter case is just a limiting case of this modified gravity theory, where you, in this action, you just turn off this last term that is, you know, your fancy curvature Kretschmann scalar term. When you turn that off, you essentially get minimally coupled scalar field. Well, with a mass, I guess you should include the potential. So yeah, I mean, you can have a code that essentially does both, where you just set the coupling in the modified gravity theory to 0. So we don't tend to do that because the whole machinery that works with this final term is actually like giant. So actually, thank you for giving me an excuse to show you the actual form of the equation. So this is what you have to put in to do the modified gravity theory, whereas putting in like a minimally coupled scalar field is super simple. So yeah, we don't tend to use the same code, but I think you easily could. I think it's nice to think about both problems together. So I've really only started working more recently on the modified gravity side, and it's really changed how I think about the wave dark matter stuff. So I think it's nice to think about both if you can, because it gives you a different perspective on things. Yeah.
All right. Yeah, we have another question here, and I see you on the back.
Hi, I was very interested in those comments that you made about well-posedness, like breaking down at some point during the time evolution. Of course, that's right, that's what happens. But my question is, how sure can you be that that is like an unavoidable effect of the theory rather than just a gauge effect? That seems very subtle to me.
It is extremely subtle, yeah. So people still debate this. So there was this interesting paper, this one that I have listed here, basically by Justin Ripley and one of his collaborators, Abhishek Hegada, and they did it in spherical symmetry. And there you can actually do it in a way that is, in a sense, gauge independent. So they claim that this breakdown that they're seeing in that case really is a physical breakdown of the theory.
Right, but it's not obvious if that generalizes beyond spherical symmetry.
Exactly, yeah, that's exactly right, yeah.
Thank you.
All right, yeah, we had one more question up there in the back. Alfonso?
Hi, thanks for the nice talk. I wonder if you can give me more details about the simulation. So both for your scalar dark matter, I don't know if you do fuzzy dark matter or your axion, what's the size of your box, and how do you set also the initial profile for your scalar field, and also for the modified gravity as well?
Yeah, so in the case of the dark matter, what we had been doing is basically just starting with the last box of this sort of panels, which is just starting with it being homogeneous at a certain value. So displaced in the potential, so then it will just oscillate like this. And then what you see is that over time, you develop this kind of swirly pattern around the binary. But that, in a sense, is not the right physical solution that you should have as your initial condition. So I think that's the concern I have about these initial conditions, is that we tend to put in things that are easy to put in, easy to type into my code and easy to solve for, in these terms of these constraints. But they're definitely not the right physical initial conditions that we should expect from millions of years of evolution in a wave-like dark matter environment. And so, yeah, I think that's a real challenge to do the correct thing there.
And the modified gravity? Also, the question is, do you solve the Klein-Gauss equation for your new degree of freedom, or you just solve the Einstein equation?
Yeah, we just solve the Einstein equation. So we start with zero scalar field. So this is obviously not this is not one of these stationary solutions for the sort of hairy black hole, but then you will dynamically grow the hair over time. But again, that's not the right physical initial condition that you're looking for. It solves the constraints, but it's just a kind of a trick to start the simulation with. Yeah.
Okay, I think we have to move on. So I would postpone any further questions to the coffee break. Katy will be here, so you can chat further.
Yeah, or ask me in the Slack.
Perfect, thank you so much. Okay, let's give a big applause to Katy again for this wonderful talk.